it, I'll let you go. You may think that I'm insane. Give me reason, then I'll take out the blame. But I'll be your fire, I'll be your courage, I'll be the sun in the dark rainy day. I'll be your highway, I'll be your smile,
IoT device
I'll
with
be
vulnerabilities, and that are projected for 2021 that there will be 25 billion devices connected to the internet. And some studies show that if only 1% of all those devices be able to use the 5G technology, they will be able to push since 10 until 50 gigabytes per second in a floating attack. And we assume that network traffic has a pattern, follows a pattern, and what is out of this pattern is an anomaly or outlier and probably an attack. And one way to detect those anomalies would be by inspecting visually the network traffic logs. But it's clearly a big challenge for network administrators and almost impossible. So one solution would be the use of artificial intelligence to automate all that process. And in this work, we propose a machine learning model that applies robust statistics, that is a field of statistics that include methods capable of dealing properly with the presence of outliers. And to build our model, we used two algorithms, robust principal component analysis and Mahalanobis distance. And our model is called RPCA-MD. Some works have already used those algorithms to detect anomalies. Youngjun applied also RPCA to detect anomalies in network traffic data. He did not use the Mahalanobis distance. And in his work, he defined a time range and the time range of the number of packets that were in the network in that time range, and he applied the RPCA to define if there was an anomalous behavior or not. Yang, as well, our work does, he applied RPCA alongside Mahalanobis distance, but he applied to image processing. His aim was to detach objects from the background because he assumed that in images, objects are anomalies and the background is the pattern. Botnet, in a nutshell, is a set of devices connected to the internet, infected by a malware, and then controlled by a bot master to perform malicious activities and attacks on his behalf. We could compare botnets to puppets because the devices are controlled by the bot master and act on his behalf. And another good analogy would be zombies because the infected devices are used to infect the others to increase the bot's army. And the attacks approaches in this work are enhanced by the use of botnets. The attacks are click fraud, DDoS, fast flux, port scan, and spam. One example of enhancement with botnets is DDoS because when you have many devices working together, there is much easier to take down a server. And also spam, when you have many devices, it's easier to spread the malware. Robust PCA, robust principal component analysis, is a method, an algorithm to decompose a data matrix to remove the noises. And here we have an elementary example of image processing to visualize what happens. Here we have the original data matrix X with some noises represented by the blue points. And after the decomposition, these blue points, the noises, are put into the sparse matrix, the S. And the L matrix represents the X matrix without the noises and with the left holes filled with the pattern around. So RPCA does a matrix decomposition and matrix completion to remove the noises. And Mahalanobis distance is a way to calculate the distance of all the samples in a distribution from the mean. It's interesting to use it when you have multivariate data, data with many attributes, features, because when it measures the distance, it considers the covariance between the attributes. And the data set we used is CTU13. It has 13 scenarios. It's a capture of real botnet traffic mixed with normal and background traffic. And the packets were captured in PCAP and converted to net flows. And we analyzed those net flows records, and we selected the most distinctive features to analyze. And those features were source port, destination port, destinee type of services, source bytes, state, total of bytes, and total of packets. And the total size of this data set is 697 gigabytes. Here we have an overview of all the scenarios, the set of attacks on each one, the protocol used for CNC communication. CNC is the command and control protocol that is used by the bot master to control the device to perform the attacks. The name of the bot used, and the rate of malicious flow on each scenario. And to evaluate our model, we used some metrics. The main metric used by us is the F1 score. That is very recommended when you have unbalanced data sets. That is our case. Our data set is unbalanced because, by definition, anomalies are very uncommon events on data. And it comprises, the F1 score comprises the harmonic mean of precision and the recall. And the score varies since 0, the worst, until 1, the best. And our model was built following this flow chart. And for each scenario, we divided the data set into a training and a testing set. The training to fit our model to this kind of data, and the testing to evaluate our model. So we start with the training, and we built our training data set with only non-contaminated data. In other words, we used 50% of all the samples without botnet flows, because it's a good practice when you are detecting anomalies. You have to train your model only with what's considered normal, and with a large amount of data considered normal, and then it will be able to detect what's anomalous. So in our training, we get this non-contaminated data set. We apply the RPCA to remove the noises, so we got a matrix, a non-contaminated matrix without any noise, totally cleaned, and we calculated the mean of all the attributes of this matrix, and we started the testing. The testing had to be a contaminated data set, and we organized it in such a way that 33% of all the samples were botnet flows. And then we applied the prediction. We did the prediction by applying the Mahalanobis distance. What we did here, for this contaminated data set, we calculated the distance of all the samples from the mean that was previously returned on training, the mean of the non-contaminated data set. We measured the distance of the contaminated data set, all the samples from that mean of the non-contaminated. And using a contamination rate, we defined a threshold that is the maximum distance from the mean for which a sample can still be considered a normal flow. And once we have this information, we could classify the samples, calculate the F1 scores, and generate the confusion matrices that are a visual way to represent the true positives, the false positives, the true negatives, and the false negatives. And it's a summary of all the results. Here you can see that the best F1 score was 0.95, and the mean is around 0.82. The results for the DOS varied between 0.78 and 0.83. And here we can see the confusion matrices. So, PortScan, we achieved the best F1 score that varied between 0.8 and 0.95. Spam and click fraud occurred always on the same scenarios, and the F1 score varied between 0.79 and 0.95. For fast flux, it occurred only on two scenarios, and both results differed a lot. The first was for scenario 5, we achieved 0.78, but in scenario 13, it was only 0.51. Because of that, we analyzed each scenario individually, and we could see that the best result was achieved when the most part of the malicious traffic corresponded to the CNC traffic, the command and control. So we could conclude that even this model is not well fitted for fast flux detection, it can detect with efficiently the CNC traffic. So we could conclude that this work succeeded in applying RPCA and Mahalanobis distance to detect botnet traffic, and compare with the work of Young-Jun, the proposed model by us, the model proposed by us, is capable of identifying exactly which moment the attack occurred, the anomaly occurred, while Young-Jun just says in a time range if some anomaly occurred. And also, we analyzed more variables. We analyzed 7 variables, and he analyzed only the number of packets. For future work, we suggest improvements on fast flux detection. We believe that this model can be extended for more types of attacks. And another good research would be the analysis of the sparse matrix to detect anomalies in it, the sparse matrix that is returned by the RPCA. So, thank you all for your attention, and we can start the discussion.
Okay, thank you very much, Eduardo. Anybody, any questions? Come on. Okay, Professor Rafael.
Thank you, Eduardo, for your nice presentation. I have just one comment that I think you could discuss is about how we do the actualization of the data set for detecting new attacks and eventually moving from some filters to other filters.
So we have to be constantly training the model to new events, to new data sets, to improve it. So if we train our data set to more situations, it will be able to deal with new data, new situations.
The need to change the data set itself because new attacks are happening?
Can you ask again, please?
Você detectou no dataset a necessidade de mudar de vez em quando as filters ou atualizar os dados em função de novo ataque?
No, I didn't do that.
No, thank you very much.
Okay, thank you, Professor Rafael. Anybody else? Okay, so thank you very much, Eduardo.
Okay, thank you.
Okay, next presentation is going to be Amplified Reflection DDoS Attacks over IoT Mirrors, the Saturation Analysis, presented by Alan Vasquez. Alan?
Thank you. Well, I have grown up a little bit, so I'll take this microphone out of here. Hi, good morning. My name is Alan. I'm a master's student at the professional postgraduate program of the electrical engineering department. And I'm here to present the results of this paper that was written by me and my advisor, Professor Dr. João Gondim. This is the outline of this presentation. I will start with a brief introduction to the subject. Then I will explain how the tests were conducted and the results achieved, ending with a discussion of the results and concluding this paper. Well, in the last years, we have seen an increase in the traffic volume of the DOS attacks. The terabit barrier has been broken, mainly due to the utilization of large botnets, which include IoT devices and malwares like Mirai. Amplified reflection of the DOS attacks have also contributed to this scenario because they intensify the traffic directed to the victim, as will be explained later. And they explore UDP-based protocols like SSTP, DNS, and so on, which are largely used in the internet, what make this a worrying threat to be aware of. It's important to point out that our paper is not about ways of detect, mitigate, or defend against those attacks. Our aim was to analyze and understand the saturation behavior of IoT devices acting as reflectors in those attacks and verify the feasibility of using these devices in those attacks. Explaining in a very simple way, this is the anatomy of an amplified reflection of the DOS attack, where you have a compromised host send spoofed requests with the IP victim of the IP address of the victim using as the source IP of the package. These requests are sent to a reflector, which is actually a host running an UDP service, like a DNS server, for example. Since UDP is connectionless and has no ways of established connection between the devices, it will process the request and send them in an amplified way to the victim. In a large attack, large-scale attack, however, an attacker would recruit hundreds of thousands of hosts and select many reflectors to generate a huge amount of traffic to the victim. There is a factor called amplify factor that is measured by the reason between the bytes received on the victim and the bytes sent by the attacker. In this case, the amplification factor was of 30 times of the original packet. In this paper, we have performed amplified reflection attacks in a controlled environment using those two protocols, SNMP and SSDP, which we find that are the most one used in IoT devices. They run on these default ports, and SNMP is used to manage devices on a network. In the first two versions, 1 and 2C, you just need to know a community string to collect information from those devices. And the public string, until now, is used by most manufacturers as a default one of the equipment. The get bucket request that was introduced in version 2C is the preferred message type for those amplified reflection attacks. The non-repeater fields is set to 0, and the max repetitions varies depending on the equipment used as a reflector. As a result, a get response message will be sent to the victim, and these get debug requests, with a single message, you can ask for an entire table of information of the device. SSDP is used to seamlessly connect devices on a network. It is based on a universal plug-and-play. And for amplified reflection attacks, we use the msearch request set up with those fields, which asks for all the services that the reflector provides, and it answers with 200 OK response for each service it has. We have used the Striker tool. It was a tool developed in Java and C to perform the attacks. It has two modules. The scan module, which looks for possible reflectors in a network, and the striker mode, where we set the victim IP and select the power strength of the attack, which is divided in 10 levels, each level exponentially increasing in the number of requests per second sent by the attacker, according to the formula above. The attack duration at each level was set to only 10 seconds, but with just 10 seconds we have achieved good results to analyze. We have created 3 test scenarios. Each scenario contains an attacker, a reflector, and a victim, all interconnected through a switch and cables to improve reliability. Each scenario you have used a different IoT device. The first one, it was used a Raspberry Pi. The second one, ADSL gateway, which also acted as a switch in the scenario. And then the third one, an IP camera. Both attackers, the attacker and the victim, were laptops, the attacker running Ubuntu Linux, and the victim running Windows. After performing the attacks, we have collected traffic in both attacker and the victim and analyzed their saturation behavior. The blue line represents the outbound traffic rate of the attacker, and the orange line represents the victim inbound traffic rate. It's possible to observe that in all scenarios, the attacker rate was very similar, and they started saturation only between level 6 and 7, which means that they were unable to generate packets at the maximum rate of those levels. And for the victim inbound traffic, which means that it's the reflect traffic generated by the mirror, we had achieved better results with Raspberry Pi because it has saturated only between levels 3 and 4. And the worst scenario with SNMP was with the IP camera. It generated low traffic rates and has saturated earlier in between levels 2 and 3, which sends only 10 packets per second and 100 packets per second. In the second scenario, we had also achieved not very good results with this reflector. It has saturated between levels 2 and 3. With SSDP, we had similar results for Raspberry Pi, but the other two reflectors presented different behavior. This time, the IP camera had better results. Its saturation occurred only between levels 4 and 5. But with the ADSL gateway, we had the worst result scenario tested in this paper. Besides, it looked like that the reflector had saturated between levels 1 and 2. What actually occurred here was that the reflector sent the replies on a fixed rate that was of approximately 28 kilobits per second, which means that besides the attack duration in the attacker has lasted for 10 seconds, here, for example, at level 3, it lasted for almost 1 hour. And after level 4, it has suffered a severe saturation and was incapable of generating any reply starting on level 5. We have also measured the amplification rates of the attacks. It looks, in both scenarios, we had a similar pattern of behavior. In both scenarios, the ADSL gateway has reached higher amplification rates, but just until its saturation, which occurred very early in the levels 2 and 3. After that, Raspberry Pi has achieved better results until the end of the tests. Well, as observed in the graphs, the results indicate a pattern of saturation that varies from levels 2 to 4. And for the attacker, it started on level 6. The results achieved in this paper are consistent with other two papers that we have analyzed and compared with our, but with some minor difference that are discussed in our paper. And two atypical behaviors were observed with SSDP. The first one was explained in the graph. The second one, was explained in the graph. They relies on a fixed rate. But the first one was that instead of replying using the default port as the source port of the package, it replied with non-default ports. It was interesting because it didn't compromise the attack. The contents of the packets were of legitimate SSDP traffic. But in scenario 3, for example, not only it was on non-default port, but also it used random high ports above 30,000. Maybe it's due to its implementation. And to conclude, we believe that amplified reflection on the DOS attacks are feasible to be performed with IoT devices as mirrors, but have to keep in mind that we have to send low probe rates to avoid their saturation. And more limited the devices were, earlier they have saturated. And a powerful attack would require a large botnet and also a careful preparation of the attack and orchestration of it. For future work, we'd like to test with other protocols like DNS, CoAP, NTP, and so on. Also test with IPv6 and Wi-Fi interconnection to see if the results are compatible with cables. And increase the number of reflectors would also bring interesting results to analyze. If you have any questions.
Thank you very much, Alan. Anybody, any questions? 5 minutes. Professor?
Thank you, Alan, for your presentation. It was very interesting. My question is, although I have well understood the economics of the attack from the point of view of the attacker, I would like to ask you about what can be the defender do with your results to counter a botnet attack?
Yeah, it's an interesting question because before find ways of defending against those attacks, you have to clearly understand how it really occurs and understand the whole phases of the attacks and find its flaws to provide how can I say, and understand its flaws, you can propose methods of defending and mitigate them.
Okay, thank you, Alan. Thank you very much again. So, any questions? No? Nothing? Okay, thank you. Okay, so this is my time. It's kind of weird, but the following paper, DOS Attack Prevention on IP SDN Networks, is from a student of mine, Awatef Ali Youssef, and I'm just like the coordinator of Awatef. So I'm going to be presenting this paper. On the agenda, we have precedent and motivation behind the name behind this work, security architecture for SDN and IPS North, results and conclusions, future works. Why we just choose to try to understand a little bit more about IPS, IDS on SDN networks? Because as we can see, we have legacy networks such as appliance from Cisco and other vendors. So what we have just SDN networks, which works as an automated network. So you need to put some intelligence in the network, such as to redirect data flows coming through a switch. So we have problems like security features to prevent some type of attacks, regardless of the attack being generated in a local area network or on a wide area network. We have to inspect packets and other types of data flows. So how to integrate a SNORT into an SDN, a software-defined network controller, to identify denial of service attack. So here we have a figure that we propose in our work, that we have a demilitarized network, integrated directly managed by a firewall SNORT. This is a firewall. We have a switch, open virtual switch on the network, directly connected to a controller. We're going to see how the data plane and the control plane is separated from this work. We have a honeynet and devices. Okay, so this is the proposed technology. As we've been leading with in this paper, of course, it is a common sense that we do not have end devices just like 100 end devices or 20 end devices. So some of the devices you can see here were implemented in a mininet, okay? And in the mininet, you can generate an amount of hosts, okay, to generate traffic into this topology. The honeynet is a honeynet implemented in the Latitude. Latitude is based at the communication network of this faculty. Firewall and SNORT, they have been implemented in Linux, okay? And the controller, we're going to see furthermore how it's going to be implemented. So what do we have here? This is very interesting because we have legacy switches, and you have the intelligence of the switch is directly connected to the legacy switch. So you have to get into the switch to make decisions or to revert some decisions. The legacy switch correctly can send and receive data from open flow switches, okay? But we have a disconnection from the control plane as what it is seen in traditional switch to have a software-defined network controller. So you have an automated controller to just interact with any kind of ports into the switch. So this is a best. So why we use RIU? This is interesting because as we are dealing with platforms integrated into Linux, what we need is to control any kind of anomaly into the network and concentrate any kind of data flow and sending all messages to the controller. The control is being implemented using Python. So as it is being implemented in Python, and we know that Python is really easy to work with. So why not implementing an IDS and an IPS, a Snort into the firewall, so that any kind of script using a Python, okay, can be redirected to the controller RIU. So that's the case why we use RIU in this work. And how it is made, we have REST calls. This is an API, really easy to deal with. So you can put any kind of command remotely from the firewall directly to the controller, and the controller sending, how I can say that, a message through the OpenFlow protocol to the switch. So the complements I've been talking about it. So we have a HoneyNet running Kali Linux. In this Kali Linux, we have any kind of attacks that can be implemented. The Mininet is used to simulate the network environment. So in this network environment, we have a lot more of hosts. We have a lot of hosts and switches. The Open Virtual Switch has been used to create a virtual switch that supports the OSI protocols, such as Spanning Tree and other ones. And the OpenFlow enabled switch counts the number of packets to match a given role. So how does it work? This is really interesting because any kind of packet coming through the port, the switch port, has to be redirected to the controller, to the SDN controller. How we do that? We have to use an OpenFlow protocol. This is a simple mechanism used to interact between the soft switch and the controller. And you have to deal with a table that has matches and actions. So if, for example, I want just to drop any kind of data coming through port number 3, so I'm going to go to the controller, and I'm going to say any kind of traffic, data flow coming through the port number 3, don't put it on the outband of another port, so just drop it. So this is how it is done. As a result, what we've been doing, we have a PC. We have a PC. In this PC, we have implemented this PC in reality. It is a host of the Mininet network. So this host is being configured via HPing. HPing is really great because if you want to test your network, if you want to test any kind of anomaly in your network, just use it, and you can implement a data flow of bytes to megabytes, any kind of situation that you want to implement. So the host in the Mininet is doing an attack. This attack has to be analyzed by the Snort with a given rule. Having the rule at the Snort, what we want is that I have to detect any kind of anomaly of data flow passing through the switch and leave the real controller receive the data or the signal information from Snort and take the correct measures. Okay, it is an automated. So an administrator has to go to the real controller, put some rules just to match and say, for example, okay, there's an algorithm saying that Snort has detected an attack. So what you should do, should you just drop all data coming from that PC or reroute this data to a HoneyNet so that I can have a fingerprinting of any kind of malicious software getting into the software, so I can put it into the HoneyNet and analyze it. How I do that? Because as the PC is on a given port at the switch, what I want the controller to do, I want it to reroute the traffic to the port where I have the honeynet and to put it there. It's just like a blacklist. It's not a real blacklist, but it's just like a blacklist and analyze what is going on. Okay? So what we've been doing as a result is just to see how long it takes. How long it takes to receive the data propagated from the PC, the attacker, to the firewall, and to detect this attack. So the line, the blue line, shows me that I have a mean deviation of 3.1 seconds of how long do I take to detect an attack by the snort in my network. But the problem is that as soon as I detect the attack, I have to use a script in the firewall by snort to send a signal to the switch, from the switch to the controller using the RESTful API on the OpenFlow protocol to the controller. So it takes a little bit more than 40 minutes to the controller to react and say, well, I have a problem, an anomaly on port 2, so I'm going to reroute this data to port number 6, for example, where we have the honeynet. And why this time of 60 seconds, 50 seconds, and 40 seconds? Because the controller, by default, the real controller, has been implemented to react to match and the configuration between match and actions to send commands to the switch is about 60 seconds. So if you put a smaller time just for the control to react to any kind of situation, you're going to be leading with a sort of flooding in the network. So as future work, we're going to have to reduce this interval, okay, and increase the amount of traffic between the controller and the switch, delaying routing decisions. This is something that we're dealing with now. We have good results. We don't have it here, but the thing is that we have to develop something that will work as seamlessly between the snort rules and the controller rules, so that we have we can deal with smaller delays on response. So this is the work we've been doing, and up to now we've been seeing related works similar to the one I'm presenting here, but none of them has addressed the case of what should I do with the data, which is considered just like an anomaly in the network, and put it into a honeynet network. So thank you very much for everybody, and questions.
As you have pointed, there is a... Oh, thank you for your nice presentation. As you have pointed, there is a question of performance that is central for the work. So I was thinking about if there is not a way to use parallel processing with multiple switches or multiple controllers to take care of the continuous flow. Have you thought about this solution?
Thank you for your question, Professor. Yes, this is an ideal question. We didn't. In fact, we didn't. And we know that, well, the controller can live with multiple switches. It is correct. So I think parallel processing can reduce the delay we're seeing, because the professor is correct. as you have a delay, what you're going to do with the attack that has been going on through a certain amount of time in port number X. So what you're going to do? Should I give a command and just say, look, drop all traffic in that port, or delay any kind of commands? So it's correct. I think we can think about parallel processing just to reduce the delay. Thank you. He's telling me that is done. Okay. Thank you. Anybody else? So thank you very much. Just one thing is that Professor Rafael just remembered me that we have 3 best papers and not only 1. So now we're going to go through the session of Power System 1 with Professor Damasceno. I'm sorry.
Hi, good morning, everybody. My name is Katia. I'm from the Federal University of Santa Catarina. I'd like to ask the authors to come here. Has every author put the presentation here already? The presentation, no? Okay, come here and put it.